Okay. Mm-hmm. Sure. Let me just open up a new. All right, so she asked on our conservation of energy, and as I told you in class, we're going to have a couple different problems about that. Probably at least two, maybe even three, where you have to calculate the energy at a particular point, or the velocity at a particular point, or the position at a particular point. So it'll probably be something similar to like what we did in class, where we have something like on a roller coaster type scenario. Tessa, did you come to the other room, or did you come straight here?
Straight here.
Okay.
Should I went to another room?
No, some other people went to 104.
Oh.
All right, so yeah, we had something. Let's do it a little bit different. Like we'll do it like this. Like let's say that we have an object. Say it has a mass of 1 kilogram, and it's at a height of say 10 meters. And let's say that this height here is 5 meters, and let's say over here at a height of 7 meters, I want to know something. So I want to know a couple of things. I want to know what is the velocity here, and I want to know what is the velocity here. And while we're at it, let's say what is the velocity down at the bottom. Now when you're attacking these types of problems, the main idea is that the total amount of energy as you go through is going to always be constant. That's what the conservation of energy says, that the energy doesn't change. So whatever energy I have here is going to be constant all the way throughout. Now if we say that the velocity is 0, or the speed is 0, at the top it's at rest, and then you let it go, and it goes through the system, then you can find the velocity and the position of it at any time, just by taking the energy at this location and then setting it equal to the energy here, the energy here, and the energy here. Now getting to your question, Bree, how do we know, I think this was your question, how do we know what is the potential or kinetic at a particular point? Remember the potential, isn't that what you asked? Something like that? The potential energy, remember, is mgh, and the kinetic energy is 1/2 mv squared. So when h equals 0, pe equals 0. All right, so in this position, the only place where p equals 0 is right here. Right? And then when v equals 0, when the speed, then the kinetic energy is equal to 0. And so the only position here where the velocity equals 0 is at this first location. That's where it's starting. And I know that because if I let it go here, I know it has a certain amount of potential energy, a certain amount of potential energy, but it has no kinetic energy. And at this point, it's going to have some amount less potential energy. So whatever the difference is in the potential energy and the total energy it had over here, it's going to have in what type of energy at this point? In kinetic energy. So it'll have some potential and some kinetic. Here it's going to have all kinetic energy, no potential energy at all. So the amount of kinetic energy it has here will be equal to the amount that it has up here. Right? And then the only other place where it might have 0 kinetic energy is when it comes up to a position over here where it stops. What position will it stop at over on this side? What height? What is it, Jessica? Right, what is the maximum height? 10. 10 is right. So it's going to come back up to where it stopped, where it started from. Okay? So it started at 10, it's going to end at 10. So if we want to know, say, the velocity at this point, I just say the energy at point 1 is equal to the energy at point 2. We'll call this point 1, we'll call this point 2. Over here, it's going to be PE1 plus KE1 equals PE2 plus KE2. So once you get that set up, it's really just algebra. Which of these is equal to 0 on this left-hand side of the equation, Sarah? Your button. Okay, over here.
Oh, no, okay.
Yeah, right.
Kinetic.
So,
I'm sorry.
yeah. So my that's okay. So our kinetic energy is 1/2 mv1 squared. And then at this location, it has both kinetic and potential. Okay? So that's going to be mg times 5 meters. Yeah, Tesha?
How does it have kinetic energy right before it goes all the way up?
Yeah, you stretched out potential energy as you wrote kinetic energy. Doesn't it have
Oh.
potential energy and not?
Yeah, I'm sorry.
Yeah.
Yeah. You're right, Tesha. Thank you. So it has potential energy, but it doesn't have any kinetic energy at the top. Right, because the velocity is 0. The speed is 0. Okay? So then, let's see, I can cancel some things out. My masses, if I divide through by m all throughout the equation, the masses just go away. And so whenever we're dealing with conservation of energy, the mass is irrelevant. As long as we're talking about systems that have no friction, which we will, that we'll be talking about conservative systems. That is, systems where conservative forces apply. Now remember those conservative versus non-conservative forces? You're likely to have a question about this as well in the exam. What are conservative forces?
Non-conservative is friction.
Right, so friction is a...
Conservative is out.
What? That don't need contact. And we only really have one force that doesn't need contact. What's that force? Right, the gravitational force. Also electrical forces, which we'll deal with. So field forces, as a general category, are conservative forces. And that's because they don't touch other objects. And whenever you touch other objects, you lose energy. Okay?
So field or conservative?
Field forces are conservative forces.
And you said gravitational.
The gravitational force is a field force. It doesn't require contact to act. Agree? That's just at location 2. So it's just a subscript to say the velocity at the second point, which is that at 5 meters high. Okay, now I can just put in numbers here. I have 1/2 of v1, that was 10 meters per second. This is the velocity that oh no, I'm sorry, shoot, I did it again. I'm sorry, very sorry. Sarah, I'll blame it on you. Yeah, okay. mgh. Alright, so our masses cancel. Very, very sorry about that. So this is g times 10 meters. That's my height over here, equals g times 5 meters plus 1/2 of v2 squared. And it's v2 that I want to know. I want to know the velocity, or the speed rather, at this point, at the very top of this jump. So if I take this and I subtract it from this side, I'm left with 5g equals 1/2 v2 squared. Then I multiply both sides by 2. That gets rid of the half there, and then I square root it on both sides. So that gives me v2 equals the square root of 10 times 10, 10 times 10, which is equal to 10 meters per second. Make sure that you're okay with that algebra. We'll see some other questions. I'll let you try it on your own, because you will have to do this, solving for these variables. Okay? Now, you want to do another example? Is that okay?
And you said this is going to be online, right?
Yeah, I'm recording it. I think I'm recording it. Yeah, I am recording it. But if you're lost, please stop me, because if I'm going too fast, then I want to not be doing that. Okay? Especially in this setting. Y'all good with this? Y'all can do this right now in the exam and ace these 2 to 3 questions. Yeah. Okay. Let's see. There aren't really many pitfalls here, except unless you accidentally write 1/2 mv squared here instead of mgh like I just did, right? But otherwise, there aren't really a lot of common mistakes that people make. People usually do pretty well on these questions. They're fairly straightforward. The values are what they are. You just have to figure out where the potential energy equals 0 and where the kinetic energy equals 0. That's really the big thing. All right, let's now say I want to know what is the velocity at this point, and I'll call this point number 3. I'm going to erase this business. And then I'm going to say E1 is equal to E3. At position 1, we only had potential energy. That's mg times 10 meters. At E3, what kind of energy do I have? Potential and or kinetic? All kinetic, right. So I only have 1/2 mv squared. My masses are going to cancel, and I'm left with g times 10 is 100 times 2. That's getting rid of this half over here. Square root of that, what's that? 14, roughly? Okay, so that's 14 meters per second. Y'all okay with that algebra? I can go through the steps. If you'd like for me to, please say so.
Can you go through steps?
I absolutely will. Just a second, Jessica. Keep that question in your mind. So here I have, let me just backtrack this a little bit. All right, so I want to solve for V. So I've already canceled the m's. I still have my 1/2 there. I'm going to go and do 10 times 10 here to get 100. That's equal to 1/2 v squared. Then I have to multiply both sides by 2, right, to get rid of this 1/2. So I have 200 equals v squared. And then I have to take the square root of both sides. And that's the square root of 200 is 14, roughly. All right? I just Okay, good question. The masses cancel here. If I go back to this part, if I just divide both sides through by m, and I can do that, right? Because as long as I do it to both sides of the equation, the masses cancel there, and the masses cancel there. Okay, so it just falls out mathematically, but it does imply then that the mass is irrelevant to the conservation of energy, how the energy is transferred. So a more massive object would see the same velocity. Great. Or whatever. Like sometimes you might have information about another point. Like for example, see now we know that the velocity here is equal to 10 meters per second. So we could compare it to point 2. Y'all want to do that just for extra practice? All right. And guys, we'll treat this as a help session, so you can come and go if you like. Like if you find that you have something else, like you have a date at 2:30 or whatever, or 1:30. We're not going to go past 2. But if you have a date, you can go. Just go quietly. I can't care if this anything. Y'all tell them what I made on my exam yesterday. A 100%. Good job, right? Yeah, I was very pleased.
What exam?
Oh, the
did you do?
history?
Yeah. I made 70s on the first 2. I have 6 total, and I figured out how to study. Yeah. They're online tests. They're only like 10 questions, so they're not a big deal. Yes. Yeah. All right. So like instead, let's say I could say E2 is equal to E3. If I were to say E2 is equal to E3, that would be mgh plus 1/2 mv squared, because at the second location, I have both potential and kinetic, and then that's going to be all at location 2 is equal to 1/2 mv3 squared. So you see, I don't have to all compare it to position 1. I can compare it to any position where I have enough information that I know the energy. Tasha?
So your equations is based off of what kind of energy you have in that location.
That's right.
I don't know which equations to use.
Right. I mean, I'm not writing them all, but I could very easily say plus mgh3, but because h3 equals 0, this term does not exist. It's just equal to 0. So I could write it out completely, mgh plus 1 half mv squared equals mgh plus 1 half mv squared, but it helps if I know which one is equal to 0, and almost always one of them will be equal to 0. Correct? And then masses cancel there and there and there. I'm looking for v3, so I have 10 meters per second squared. That's my acceleration due to gravity, times 5 meters, plus 1/2 of v2 squared, which was 10 meters per second squared. That is this quantity, which we had already solved for. That's the velocity at the top, is equal to 1/2 v3 squared, 50 plus 50 equals v3 squared. I'm multiplying both sides by 2 now to get rid of this 1/2. And so that's going to, v3 then is going to be the square root of 200, which we already know, but that's equal to 14 meters per second. So you see, it doesn't matter what points you're comparing them to. I forget who asked that question, Jessica? But as long as you know enough information to find out what it is that you're looking for. Okay? That's conservation of energy. Now, we're also going to see conservation of energy in terms of elastic potential energy. Can we go ahead and do that while we're on this topic? Because this will also come up, and you'll also have questions about this as well. Can I go down to the next slide? We'll get into this on next class, but elastic potential energy, I think I call it PES, is equal to 1/2 kx squared. So this is like the rubber band. K is the spring constant. And x is the elongation. So K describes how stretchy the material is, right? If it's not very stretchy, you have a big K, so it holds a lot more energy, right? Like those big thick rubber bands, they have a big or small K. Big K, right? And so if you stretch them, they go a long ways. But those little dinky rubber bands, they have a small K because they're not very stretchy, right? So that's the spring constant, and the elongation is just, how much does it stretch? How much do you stretch it? Yeah, I mean, slinkies are springs, so yes, they have a certain spring constant. We'll do a whole lab on springs where we measure how much they stretch by their elongation and the forces involved. Okay, but yeah, slinkies are a slightly more complicated version of this. 3? Yes. Oh, S is like it's short for spring, because we're talking about springs. But this is elastic potential energy. Elastic potential energy. So, for example, I could say, okay, good question. We're going to do this in class, but let's say I shoot a rubber band up in the air. And this rubber band has a K equal to 10 newtons per meter. That's the spring constant. And it has a mass equal to, let's just make the numbers easy, okay? Mass equal to 1 kilogram. That's a whopper of a rubber band, okay? But let's just say, just to make the numbers easy. So the mass is 1 kilogram. So I shoot a rubber band straight up. I stretch the rubber band 0.1 meters from equilibrium. All right, that means when it's not stretched, that's equilibrium, and then 0.1 meters means I stretch it 0.1 meters extra. That's 10 centimeters, so I'll stretch it back pretty far. All right, so I stretch it 0.1 meters from equilibrium. How high does it go? This would be a good test question. All right, we're going to do a whole little thing in class with this. All right. So what I have here is I have a rubber band. I stretched it. It's going to go up. It'll come back down. All right, I want to know what is this height. Okay, I know that down here it has a certain amount of elastic potential energy. And then up here it has a certain amount of gravitational potential energy. I want to know the height. Okay. So I can say then the amount of elastic potential energy down here will equal the gravitational potential energy up here. Because that total amount of energy is always going to be the same. And so I know that down here, the gravitational potential energy equals 0. And up here, the elastic potential energy equals 0. I also know that the kinetic energy here equals 0. And we'll talk about this in just a minute, but for now, let's just say that the kinetic energy down here equals 0. Sort of true, sort of not true. I'll tell you what I mean in just a second, okay? So I would say that PES would equal PEG. That is the total amount of elastic potential energy. How much energy I stored up in that rubber band down at the bottom is going to equal the amount of energy stored up in the gravitational energy at the top. And so this would be 1/2 kx squared equals 1/2, excuse me, no, not 1/2, equals mgh. Okay, and then I solve for h. I'm going to divide both sides by mg, and that'll give me h. Let's just go ahead and put those numbers in. K was what? 10. So I have 1/2 of 10. That's in newtons per meter. That's the spring constant. That will almost always be given to you, or you'll be asked to find the spring constant. But in this case, it was given. X is 0.1 meters. Remember, that's squared. Now, in this case, our mass is relevant. It doesn't cancel out in this case when I'm comparing elastic potential to gravitational potential. All right, so my mass then is, 1 kilogram. That's funny. And then times g, which is 10 meters per second squared. All right, so I can simplify this a little bit. The 10s cancel out. 10 over 10 is 1. I can just get rid of that 1. So this is just 1/2 of 0.1 squared, which is what? 0.001.005 meters. Is that right? That's right, isn't it? Yeah, 0.005. Okay? So that's how high it goes up. The numbers there are all wacky. It's just sort of as an example. Okay, good question, Bree. At the top, the kinetic energy equals 0 because, it goes up and it stops. That's right, Sarah. So up at the top, V equals 0, and so the kinetic energy equals 0. We'll work a problem in class next time where you're throwing somebody up in the air, and we'll talk about that as well, okay? Tasha?
Can you explain why is it 0 at the bottom?
Okay, yeah, so that's another thing. So really what's happening here is you have your rubber band that's stretched out and has a certain amount of potential energy, but as soon as you release it, it leaves your finger, and its elastic potential energy goes to 0, and all of it goes into kinetic energy. So at this location, like right after you release it, you also have this goes to 0, and the kinetic energy becomes 1/2 mv squared. So no longer is the speed 0. Now the speed is at its maximum value. We can figure out what that maximum value is because now we can just say 1/2 mv squared, that's the kinetic energy at the bottom, is equal to mgh. Does the potential energy at the top. Masses cancel again. Looking for V. Multiply both sides by 2. So V is equal to the root of 2GH. Uh, 0.01 times 10, I don't know what that is. It's, 0.3. Right, so yeah, 0.3 meters per second. Do y'all follow what I'm saying? That last potential energy is immediately converted to kinetic energy, and then that kinetic energy is converted into potential energy. We'll do a similar problem next time that's related to that, the cheerleader problem. Yeah.
So,
It's
kinetic energy,
Brandon. Yeah, Brandon.
the kinetic energy will be equal to the potential energy of gravity, the gravitational potential energy. It won't be equal to the spring potential energy.
It'll be equal at the bottom. Well, yeah, it'll be equal to all of them, right? So there are 3 scenarios here. It's sort of hard to see it, but right here, just before you let it go, it has elastic potential energy. Immediately after you let it go, when it's right here, it has no elastic potential energy, but it has all kinetic energy.
And that kinetic energy cannot be equal to the spring potential energy.
It is equal to the spring potential energy,
So you could,
but not at the same time. It's transferred into kinetic energy.
And then potential energy again, and then it's kinetic energy. So
Right.
just-
Yeah, and then, you know, at some point in between here, it has both gravitational potential energy and kinetic energy, which is similar to is basically the same as the previous problem we were around the roller coaster deal. Okay? Is that clear enough? Tasha?
Why did tens cancel when you actually did the math? Is it because of the units? The 10
No, it's not the units, it's just right here, you mean?
Yeah.
Oh, just because I have 10 over 10. So
I know.
I just divide this 10 by this 10, and then that's equal to 1.
Okay.
Alright. Alright. Yeah, a lot of the algebra is similar for these problems, so just with practice you'll get better at doing the algebra. But I understand that, you know, if you haven't done it a lot, then, you know, you haven't done it a lot, so you just need to become more familiar with the algebra and how it works. Dealing with the squares, dealing with the halves, all that business. Alright, how y'all on work, with the work stuff?
can we do a couple of these problems?
Yeah.
Basic work problems.
Mm-hmm. Yeah, let's say, let me think of something. Let me see if we have the internet back. Oh, we do. Okay, good. Let's look at some old test questions, because that'll probably be the best way. Yeah, that's a good picture. Volleyball. Y'all use this? It's a little sheet. Isn't it nice? Yeah.
I did not see
Yeah, so this has all the questions on the test broken down by chapter. All right, let's go back to 2012, exams 2 and 3. Oh, this is a good one. Let's look at number 21 here. So this is sort of a work problem and a kinetic energy problem. So I have a this is a fall 2012, exam 2, number 21. I have a 2 kilogram object that's initially at rest. I push on it with a force of 12 newtons over a distance of 3 meters. And then what is the velocity of the object? So I have a 2 kilogram object at rest, so this is my object here, the velocity equals 0, and then I apply a force to it of 12 newtons over 3 meters. So I can find the work that's done by that force. It's equal to force times displacement. That's 12 newtons times 3 meters which is 36 joules. That means I've done 36 joules of work on this object. It was initially at rest. By pushing on it with 12 newtons over 3 meters, I've given it 36 joules. Right. Then I know from the work energy theorem that work is equal to the change in energy. In this case, all the work that I'm doing on the object is increasing its kinetic energy. I want to know the velocity. So I'm going to take that work, 36 joules, and I'll set it equal to 1/2 mv squared. That's going to be 36 equals 1/2 of the mass, which is 2, times v squared. 1/2 of 2 is 1. I take the square root of both sides, and v is equal to 6 meters per second. So here a two-step problem. First, calculating the work that's being done, and then recognizing that the work is all transferred into energy, in this case, all kinetic energy, and then solving for the velocity. Good on that? Okay, let's try another one. There was another one back up here. Can I take this away? Let's try this one.
22 on our test.
Yeah. It was D was the answer. Horrible. Horrible. Yeah. Yeah, this is 2012. Fall 2012. All right. How about number 19? Let's try that one. We did this one similarly. Like on these questions, you know, shouldn't get these questions wrong because it's really just plugging in the right numbers, okay? And the numbers are all given there. It's just knowing the equation. And there aren't that many equations, by the way. I'll write them down for y'all. Just maybe you can do a little card or whatever and start, I don't know, pasting up to your mirror or whatever. So here our work is F times D times cosine of theta. Our force is given, it's 12 newtons. Our distance is given, is 6 meters. And then our angle is given, it's 60 degrees. All right, so that's 12 times 6, which is 72, times the cosine of 60, which is 1/2. So it's going to be 36 joules. Huh? It is always going to be cosine. The reason you know that it's cosine, if you care, if you don't care, it's okay. But if this is my displacement, this is my force in this case, this is my angle theta, I want to know the component of the vector that's in the same direction as D. That's going to be fx. So I want to know the x component of this vector, and fx is equal to f cosine theta. And to find the work, I multiply this times this. So that's where that equation comes from. It's the distance that it moves times the component of the force that's in the same direction as the distance. It's always going to be cosine. It's always going to be the angle that's given. Nothing fancy about that. All right? And just write down the equations that we have. Work, FD cosine theta. Gravitational potential energy is mgh. Kinetic energy is 1/2 mv squared. Elastic potential energy is equal to 1/2 kx squared. Another thing that we haven't gotten to is the force of a spring is negative kx. So if you pull on a spring a certain distance, it exerts a force F. If you pull it by a distance x, you feel a force F. All right, I can work a problem like that in a minute. Is that everything? Can I see your book? Oh, and then there's power as well. Fs is equal to negative kx. Oh, and what was the other thing I said? Oh yeah, the power. Power is equal to energy over time. Or I can say work over time. Just because, you know, power, energy, and work, they're the same. They're a little bit different, like, sort of how we think about them, but they're basically the same. If you do work on an object, you change its energy. They're the same units. They're the same. So those are all the equations. We're starting to get a few more equations. When we hit chapter 7, I think I gave y'all an equation sheet, if I'm not mistaken. Is that right? Have y'all seen? There's an equation. Yeah, let me double check that. That equation sheet is online. It's right here, yeah. Yeah, chapter 7, we start picking up equation sheets, because then, you know, my brain can only hold so many equations. I think y'all apply the same. Alright? Anything else in particular, something that hasn't settled well? This chapter, I wouldn't say it's easy, but I think it's certainly easier than chapter 4. There's sort of less process than we've seen in chapter 4. More just sort of simpler questions. That's good, right? Chapter 4 is a humdinger, so is chapter 3. Tasha?
Whenever you drew the, was it like the graph kind of this, I said, how did you know that it was kinetic energy down here?
Okay, that's a good question. Let me go back to that.
And then you said it was here.
Yeah, so she asked right here, how do I know that at this location I only have kinetic energy? Okay, that goes back to this line that I drew. At the bottom, at this is the point that I call H equals 0. Okay, and at that point, if H equals 0, since PE equals mgh, the potential energy equals mgh, then my potential energy there is 0. And so if the potential energy is 0, then it has nothing but kinetic energy. It only has kinetic energy. Because in this situation where there's no springs, everything is just gravitational potential or elastic potential. Jordan?
Okay, if your whole situation started at point 2, would it still have both potential and kinetic energy?
No, if your velocity at point 2 was 0, it would have no kinetic energy.
It would only have potential.
Right. Yeah, in this case, because I said v equals 0, it has no kinetic energy. But I could say the velocity initially is 10 meters per second. And then you would just say, well, mgh plus 1/2 mv squared. When you see one of these problems, you just want to go through and say, well, the velocity here is 0, the h here is 0. You first want to assess every point, and does it have potential and or kinetic? Every? Right. That means that she said that, let me clean this up. I want to do it right here. At the very bottom here, I said in class that the kinetic energy is equal to its maximum value. That means that the kinetic energy fluctuates, right? Like here, it has no kinetic energy. The kinetic energy increases, while the potential energy is decreasing. And so here, it's at its maximum value. It doesn't get any higher than this. And then the kinetic energy decreases, while the potential is increasing. And then here, the kinetic increases. It's at its maximum value here. And then when it comes back up here to 10 meters, the kinetic energy is what? 0, right? It goes away. So it's at its minimum value, or its 0 value. At its maximum. Does that answer your question? Let's try another question, though. Let's say that I have a 10 kilogram box. I drop at a distance of 5 meters onto a spring that has a K value equal to, I don't know, 2. Right? How much does the spring compress? This is another good test question. I'm going to go back to my office and write these down. Okay. Right, how much does the spring compress? Should have, that would be a good extra credit question. I could have y'all write test questions. I did that once. Like I told students if they wrote a question, then I would select 1 or 2 to put on the test. But nobody did it. So I was shocked. Like, I had 100 students something like that. Maybe it wasn't presented well enough. I need to wrap it up in a bow. All right. So how much does the spring compress? How would I do this? So I first want to assess what are the energies at particular points. At the top, what do I have? 0 what? 0 kinetic, right? And what do I have the maximum of? Potential, what kind? Gravitational? Right, okay, gravitational. So at the top, I only have gravitational potential. Now at the bottom, I have kinetic energy just before it starts compressing the spring. But I'm asking how much does the spring compress? So the box falls, it lands on the spring, and then it compresses it a certain amount, right? So at the bottom, what kind of energy will I have?
You have the spring.
Okay, I have the spring potential. Now you're right in saying that there's kinetic energy, right? But then it hits the spring and it stops. So the kinetic energy goes away. So at the bottom, I just have potential energy of the spring. Y'all follow me on this? This is sort of at the reverse of the rubber band problem. All right, so I have PEG at the top equals PES at the bottom. That's MGH equals 1/2 kx squared. And I want to know x. However you want to do that, you can put in the numbers or you can solve for x. I'm going to go ahead and solve for x here. I'm going to multiply both sides by 2. That gets rid of the 1/2. And then I'm going to divide both sides by k. Right, that gets rid of the k right there. And so I'm left with x is equal to the square root of 2mgh divided by k. It's 10 kilograms, 10 meters per second squared. It's 5 divided by k, which was 2. 200, 1,000, square root of 500.
22.4.
What is it?
22.4.
22 meters. It's a big spring. Yeah, the numbers don't really make sense, but I would have numbers that were more reasonable. Actually, there's something else a little more complicated going on here, is that with a compression that big, you would have to consider the change in gravitational potential energy as well. But if it's a very small compression, then you wouldn't have to worry about that. Y'all follow what I mean by that? Like, this is such a big spring. I didn't mean for the number to come out this big. But if it's such a big spring, as it's compressing the spring, the gravitational potential energy is also going to decrease. But that's a lot more complicated than what you're doing. Okay? Like, we'll assume that it compresses very little. You follow what I'm saying? Okay. All right. What else? No. That's this chapter.
Like you just said, if it only compresses a little at the bottom, that would mean that would be a smaller spring.
Yeah. Like, I should have made K a lot bigger here. So K probably would have been like 2,000. And then this number would be really small. So if it doesn't make sense what I'm saying, just don't worry about it. I don't want to confuse it. But if you have a really big spring, then when the block hits the top, it still has gravitational potential energy, and then it loses that that. And so there's an interchange between gravitational and elastic potential energy as it's compressed in the spring. And that's more complicated.
So
What
that
is-
was.
They're down a lot.
Yeah. I'm sorry, forget.
Oh.
Oh, I'm not asking the height. Here I'm asking how much does the spring compress?
I know, but so why at the bottom wouldn't the potential energy be zero?
The gravitational potential energy at the bottom is zero. It's the elastic potential energy. See, this object falls, it has gravitational potential energy here. It falls down to the spring and compresses the spring, and it converts all its gravitational potential energy to elastic potential energy. This is just like the rubber band problem, it's just in reverse. Instead of shooting something up, I'm dropping something from some height. I think the rubber band problem is better. Yeah. Okay. Let's see what we got here. Okay, how about this? If you're gonna see some questions like this where I ask you, can y'all see this? The text of this? Not really.
But it,
I don't think I can zoom in with this browser. But it says if both mass and velocity are tripled, so mass becomes 3m and velocity becomes 3v. I increase those both by a factor of 3. How much does the kinetic energy? You'll see a question like this, one or two, where you just have to think about the relationships. The kinetic energy is 1/2 mv squared. If I triple v and I triple m, then my kinetic energy is increased by what factor? Not 9. What is it? No, not 3. Not 6. 27, yeah. Right, because look, I square this 3, right? So it's actually 3 times 9 by a factor of 27. Be prepared for that, okay? How the kinetic energy changes with different changing quantities. So let's say I drop an object from a height h, and when I drop it from a height h, it gets a velocity v. Okay? What if I drop that object from twice the height? What is its velocity now? Well, I say mgh equals 1/2 mv squared. If I drop it from twice the height, how do I make the right-hand side of this equation be the same? Not 2, it has to be what? Not a 4 either. A what? I think you're thinking the same thing. I don't think the right words came out of your mouth, but
Not square roots.
the square root, right. So here I would need a root 2, square root of 2. So if I drop it from twice the height, I get root 2 the velocity, 1.4 times the original speed. I think we had a similar question, yeah, where you take, yeah, in the concepts. A lot of people missed it, but you can see a question like that as well. Okay? Let's do this last question, and then we'll clear out. Unless y'all have any other, is this okay, doing these questions like this? Is this helpful for you? Okay, good. All right, let's do number 3. It says a rock is thrown straight up with an initial velocity of 15 meters per second. How high will the rock rise? So I throw a rock up in the air. It goes to a certain height. I know down here v is equal to 15. And I want to know what is h. Now we did this problem with kinematics, and you can certainly do it that way. We've done it, but it's a lot easier to think about energy. So at the bottom, it has potential or kinetic energy at the bottom?
It has
Right, only kinetic. Because at the bottom, H equals 0, potential energy equals 0. So kinetic energy at the bottom equals potential energy at the top. Because at the top, remember, V equals 0, so kinetic energy equals 0. And so I can say 1/2 of m times v squared, which was 15, equals m times g, which is 10 meters per second squared, times h, which is what I want to know. My m's cancel. I get 113. Oh, that's not right. Did I do that wrong? 15 squared, half of that. Oh yeah, no, 11.
11.5.
Yeah, 11.5. I was using 9.8 in this test, but so H is 11.5. Actually, this works out to 11.3, but the right answer is 11.5. If you use 9.8, it comes out 11.5. Okay, that's similar to problems we've already seen. Oh, what is the unit of work dimensionally of these? Remember, work is force times displacement times the cosine of the angle between them is d, right? So newtons times meters. And then I could also ask you a question, I did this in class, what are the basic SI units? Newtons is mass times acceleration, that's kilograms meters per second squared, times meters. So the basic SI units are kilograms meters squared per second squared. You'll start seeing questions like that cropping up on tests to come this semester, of which we have 2 more and a final, so lots more time to do well. All right? All right, guys, we'll wrap up there. Glad y'all could make it. Hope it's time well spent for you.